Okay. Okay, so I promise no equations. This is the non-equation part of the talk this morning. But I just want. Okay. So yeah, we need to be done by 5 because Max is giving a talk at 5. So Max, make sure you let me know. I can stop anytime, actually. So this is a very light talk. I don't want to be serious at all, and the first thing I want to do is just talk about the primary constraints we have on mantle convection. And what I mean really is what kind of constraints do we have on the understanding the large-scale structure of mantle convection. Of course, in reality, we have tons, hundreds of constraints. So these are very loose. The first one is plate velocities. So that's probably our most direct evidence of mantle convection, and that's that plates move at the surface. And they move about in the order of centimeters per year. Now, the problem is we don't understand whether plates are the top surface thermal boundary layer of a convection cell or not. They should be on average, but we don't know if that's the case everywhere. In fact, if you have a planet like Venus or Mars, which is most likely undergoing convection beneath their surface, but they don't have any plate tectonics, you wouldn't be able to use. Those are examples of planets where the plate velocities are not related to the convective velocities. But on Earth, we think there's some relationship. We don't know if it's a direct relationship or not. But it provides some constraints. Heat flow. So it's around 44 terawatts globally, and I've heard the number 46 thrown around at this meeting, so maybe this needs to be revised a little bit. But basically, in the oceans, we have around 100 milliwatts per meter squared coming out, and that depends on how old the ocean is. And on continents, we have about 60 or 70 milliwatts per meter squared. So this provides us with some budget or some estimate of how much heat the mantle is able to get out. Transition zone. There are seismic discontinuities at the 410 and 660 and maybe others. And mineral physics indicates that these are related to phase changes. In the early days, these seismic discontinuities were used as evidence that the mantle is layered. But now that we know about the phase changes, that's not certain anymore. Viscosity. This is probably the one thing that's most weakly constrained in the Earth. We think we have a pretty good handle on the upper mantle viscosity from postglacial rebound, and that's around 10 to the 19 to 10 to the 21 Pascal seconds. However, in the lower mantle, the uncertainty is much greater. And that's because our estimates of lower mantle viscosity mainly come from inversions, where you assume a radial viscosity profile, and you do some type of modeling and see what matches the geoid, and do a best fit to find the radial viscosity. The problem is we don't know what that radial viscosity means, that it's a 1D function. We don't know if it's relevant to actual mantle viscosities or not. We think viscosity in the mantle is very heterogeneous. Hot things should have lower viscosity, and cold things should have higher viscosity. And we know there are hot and cold things that are distributed very heterogeneously through the mantle. So if you give me an average mantle viscosity at a certain depth, what does that really mean? It's not so clear, particularly since viscosity varies exponentially with temperature. Oceanic lithosphere can sink into the lower mantle. This is a huge piece of information that we have. And here's one of the older tomography models that shows the Farallon Slab sinking beneath North America. So here's a map view. So this is Grand, 1997. Here's a map view. Here's the cross-section line. This is Pwave Tomography, and this is S-Wave Tomography. So blue represents faster than average wave speeds, and red indicates lower than average wave speeds. And I guess yellow is right in the middle. And the idea is if things are cold, waves should move faster through them. And so that provides evidence that what we're seeing right here is the Farallon Slab. So it's a slab that used to subduct beneath western North America. That ridge has been subducted. Now that boundary is the San Andreas Fault. but we think this slab is descending still in the mantle beneath us. And the bottom of that slab is somewhere in the Atlantic area right now. And we see that both in S-wave and Pwave tomography. Now, yeah, that's the interesting thing about seismic tomography. They always point out the things that we think we know, and then everything else is like, oh, artifacts. So I used to always ask about stuff like this, like, what's that? And it's artifacts. Okay. Now, I've heard rumors that this picture was carefully crafted to get the right angle to see this slab. I'm not sure if that's, yeah. 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 So you can't trust seismologists. Here's a more recent tomography model. This is a Pwave tomography model, I think, from Rob Vanderhill's group. And there are many cross-sections from Central America and South America, as well as the Western Pacific. And we talked a little bit about this morning. And most of these cross-sections, all of them, I guess, you can see this faster than average material, so probably slabs, because we know we have subduction zone here, sinking into the lower mantle. So this bottom dashed line is the boundary between upper mantle and lower mantle. And these slabs descend into the lower mantle. And these are the ones we talked about earlier this morning. In the Western Pacific, you have some slabs that seem to be resting on the lower mantle. We don't, like I said before, we don't know if they're really resting there, or because this is just one snapshot in time, it could look like they're stagnant. But we really don't know. It's a really interesting problem that we need to figure out. And here's another one here. But the fact that these sink into the lower mantle provides a lot of information. So we know slabs can get down there. Yeah.
There are other E-velocity models that don't show that.
Oh, microphone.
There are other P-velocity and S-velocity models that don't show that, for example, the slabs in South America are going all the way to the Core-Mantle boundary. Fukawa group has been working for 20 years on this problem of velocity anomalies in a slab, and the only thing that they see is that if the slab penetrates 650, it then flattens at 1,100 kilometers. So there are papers, with exception maybe of this one cross-section through, does not have any subduction zone, that the anomalies go below 1,000 kilometers.
That's a good point. Maybe we should be more careful, perhaps, and not too excited. It would be interesting to have there been any review papers on this topic? It would be interesting to see what the collection, if you look at all of the different studies.
There was a review in 2009 by Fukawa and his co-workers in, or whatever it is, advances in, or annual reviews.
And there is a more recent one coming out in the treaties on geophysics.
Oh, okay. Yeah.
Are you looking at the cross-section like Fukawa in Central America? It goes pretty deep.
So deeper than 1,000? Oh. Another piece of information that's really valuable to geodynamicists is that the surface chemistry, geochemistry, indicates chemical heterogeneity within the mantle. So if the geochemists are out of the room, that would be okay. But if they're here, they should forgive me. This is a very basic view. But to a geodynamicist, this is geochemistry of the mantle. Basaltic crust is created at divergent boundaries. And if you look at the trace element chemistry of that basalt, it looks like it's derived from a material that has melted before and Bill talked a little bit about this yesterday, I think. And we call those, we say that if that's the case, we say that's depleted in incompatible elements. And I'll talk more about that in just a moment. There are other places where we get basalt volcanism around the world, and these are places called hotspots. So if a hotspot is anomalous volcanism away from plate boundaries, usually, not always. Iceland is on a plate boundary. We don't really understand why we have hotspots. They seem to be in the middle of plates. You get a lot of basaltic volcanism. And if you look at those basalts, the trace element chemistry indicates that they are less depleted or perhaps enriched in those incompatible elements. So that indicates that they're coming from a fresher source, perhaps. So here's a plot by Al Hoffman, very similar to the stuff Bill showed yesterday. Everything's normalized to a primitive mantle. Here's a list of elements in order of their compatibility. So these are elements that are happy to be within the solid, and these are elements that would prefer not to be in the solid. And so when melting occurs, elements toward the left will go into the melt, and elements toward the right, some of that may go in the melt, but these are happy to stay in the solid. And so if you take a primitive mantle and you melt it, you expect the melt to be enriched in these things. So you expect the line to go up here. But when we look at morbs around the world, so basalts that are formed at divergent boundaries, at ridges, we see a line that looks like this. And it's relatively uniform. Morbs look similar around the world, supposedly. And they're depleted. You know, we expect a trend like this if they were being melted from some primitive mantle, but the trend comes down here, so that indicates that mantle, the source for those morbs, has already been melted. It already lost its incompatible elements, and so now it's melting again, and there aren't many incompatible elements to go into the melt. If you look at these other dots here, these are from different hotspots. I guess there are 3 different hotspots around the world: Hawaii, Tristan, and Tubai. These are less depleted. So Hawaii it doesn't look too different from Morb, but this is a log scale. And these look like they're enriched in incompatible elements. Shown here is continental crust, too, in yellow. So I guess in summary, morbs and oibs have the same bulk chemistry, but their trace element chemistry differs in the concentrations of incompatible elements. So we think morbs come from a source that's melted before, and oibs less so. So to put that into, why would that matter to a geodynamicist? Well, we don't really know what causes hotspots, but the best hypothesis that we have so far is that they're caused by mantle plumes. We haven't really conclusively seen a mantle plume, so it's still a hypothesis, really. But the idea is that in some thermal boundary layer deep in the mantle, a plume forms, it rises to the surface. The plume head may form a flood basalt in the beginning, and then after that you have a track of volcanoes. One reason that I believe in plumes is you always see them in geodynamical models. It's a consequence of whenever you're heating a fluid from the bottom, you produce thermal instabilities, plumes. So the surface geochemistry is really an integral of chemical heterogeneity in the mantle, and geodynamicists for many years now have constructed many hypothetical models based on that geochemistry, and they all have one thing in common, and that's that they have roughly 3 components to them. So everything in green here represents the morb source. So depleted mantle that has melted before, and that's mantle that provides the source for mid-ocean ridge basalt. So when this melts, it forms a morb. These models all have purple stuff, and this is primitive mantle, which is high concentrations or high ratios of primitive noble gases to radiogenic noble gases. Like, for example, helium-3 is a primitive noble gas, and these ocean island basalts typically have higher helium-3, helium-4 ratios than mid-ocean ridge basalts do. And these models also include blue stuff here in these pictures, these cartoons, and this represents crust, oceanic crust that has subducted into the mantle. That's one thing we do know that happens. We know lithospheric crust sinks into the mantle, so it must be down there somewhere. So the general idea is that mid-ocean ridges are formed from the melting of this green stuff. Hotspots are caused by mantle plumes. Those mantle plumes rise from a deep thermal boundary layer, and somewhere along the line, those mantle plumes entrain all of this stuff, purple stuff, green stuff, and blue stuff, and bring it to the surface at ocean island basalts. Now, we don't know, the geochemistry doesn't tell us which of these models is correct, but these are just hypotheses that we have. Yeah.
It's light blue ERC versus the dark blue.
So ERC means enriched recycled crust, I think. This dark blue just represents a thermal anomaly. It's a slab. So, yeah, I guess it's not. Paul Tackley should have been a little bit more consistent there. But so blue just represents cold stuff, and he didn't really apply a chemistry to that correctly.
Is it supposed to be an earlier crust? Is it supposed to be ancient crust or something?
You can think of it as all crust. You know, we're not getting into details. And you know, you can take these hypotheses to higher and higher levels of having an Archean crust and modern day crust and stuff like that. Here, it's just crust. It's down there somewhere.
So Alan, the green, the depleted mantle melted down.
Yeah.
Can I think of that as what?
Oh.
Sorry.
Can I think of the green DMM as what was previously magma ocean? Is that what is meant by had been previously melted?
I don't think so.
No, it means it had mid-ocean to salt taken out of it. Yeah. Well,
I mean, is there like how many times it's been melted?
crust taken out of it. Yeah.
Okay, so
It's been processed through a mid-ocean ridge
and
and beyond.
beyond.
Yeah.
So all those highly siderophile elements that we had been looking at aren't plotted on those.
On the previous, I
spiders.
don't think so.
They weren't on here, right?
No.
I mean, what would they look like?
They don't behave so nicely as a rare earth element. As Rich was saying, there are these other tricky phases. They're not typically measured by the same people. I would say that's a big reason, right, Rich? Like the people who measure PGEs on mass specs they're not typically done by routine laser ablation work or routine solution ICP-MS chemistry. So you could plot them on there, but
How would they plot?
So if you add DMN and comment across back together, it will be primitive. That's the way it works.
but they plot way depleted because they've been extracted
By the core.
right?
Would they be primitive mantle in terms of the noble gases as well?
No,
Just in terms of the.
yeah. It's about
Okay, so it actually takes geophysics to try to discern the structure. The geochemistry gives us a good idea that there are different things down in the mantle, but to discern which of these cartoons may be occurring, if any of them, we need to rely on geophysics. Seismic tomography provides some of the best evidence, and you've probably heard already, and maybe we'll hear a lot during the rest of CIDER, these things called the large low shear velocity provinces. This is a seismic tomography model by Jeroen Ritsema, S20 RTS. And this is a map 200 kilometers above the core mantle boundary. Blue stuff represents areas where shear waves are faster or are higher than the average shear wave speed at that depth. And the red areas are areas where the shear waves are, shear wave velocity is lower than the average. And these blue areas are thought to represent, or are thought to be caused by paleo subduction or slabs that subducted a long time ago and are now sinking to the lower mantle or perhaps at the right at the core mantle boundary now. These regions are called the large low shear velocity provinces, and we spend a lot of time right now trying to understand what those are. Here's a 3D view of that same tomography model. You can see those large low shear velocity provinces extend several hundred kilometers up into the mantle. Here are all of these blue regions around them where we've had subduction in the past. And finally, seismic studies hint that the large low shear velocity provinces are compositionally distinct from the surrounding mantle. In the early days, we just thought of them as thermal, like large mega plumes. But many seismic studies have been performed that indicate that the bulk sound in the shear wave velocity is not correlated in a way that you would expect for a homogeneous material. To me, I think some of the most convincing evidence that these are compositionally distinct comes from travel time and waveform studies, which indicate that these have sharp gradients along the margins. And these so in the background here is seismic tomography. This is a different tomography model. This is a tomography model by Steve Grand. And these black lines summarize travel time and waveform studies performed by various groups listed here that find a broadening of waveforms, for the waveform modeling studies at least, in seismic rays that penetrate these edges. So basically they find sharp gradients in these areas marked in black. And it's likely that if you have a really sharp gradient in elastic wave speed, that's caused by a change in composition. We expect thermal anomalies to be much more gradational and not produce such sharp gradients. So there are various hypotheses that we have for the cause of those large low shear velocity provinces. And I mentioned in the beginning of my talk this morning that each of these hypotheses, each of those cartoon models I showed, will have different consequences for many things that we need to understand about in the mantle. But one of those, so I'm just putting together a few categories of hypotheses. Within each of these categories, there are many sub-hypotheses that you can deal with and play with. One is that they're thermal structures. So they could be large mega plumes or perhaps clusters of smaller plumes that when viewed by seismic tomography, they look like a larger, many little plumes may look like a large LLSVP because seismic tomography has a lot of blurring and smearing inherent to it, to the process. And this doesn't explain the sharp margins along the edges. So I like to expand upon this hypothesis and say, well, you can have thermal structures causing the large low shear velocity provinces, but you still need some compositional heterogeneity in there. Maybe the compositional heterogeneity isn't forming those structures, but I think you still need compositional heterogeneity to explain some of the seismic observations in these areas. Another hypothesis is that they're caused by thermochemical domes or superplumes. And so these are intrinsically more dense structures, usually on the order of 1 or 2% more dense than the background mantle. But when they heat up, even though they're more dense, when they heat up, thermal expansion causes them to become less dense than their surroundings, and they rise up through the mantle. And as they rise up and cool off, they become more dense again because they're cooling, and they can sink back down. And these can rise and sink several times over geologic history. So this is one hypothesis for the cause of large low shear velocity provinces. So here's a cartoon hypothesis, and here's motivated by some laboratory experiments. So these are experiments done in a big tank with different materials in there. Another hypothesis is that there are thermochemical piles caused by the accumulation of oceanic crust. Mineral physics experiments have shown that basalt becomes more dense than the surrounding mantle at high pressures. So as you subduct oceanic crust into the mantle, it can become more dense than the surrounding mantle. And if you can separate it from the lithosphere, perhaps it can accumulate in these areas beneath Africa and the Pacific. And finally, the last hypothesis I'll show is that they are thermochemical piles of some primordial origin or formed early in Earth's history. And these behave very differently from those piles I just showed a moment ago. And this is probably the most popular hypothesis right now, but one of the reasons it could be the most popular is because it's for sure the simplest to model. I mean, there are the least number of complications to model such structures. But this is, so and I'm going to leave off with a, yeah. Yep.
So how should we interpret cartoons like on the left? Because in the tomography images you see perturbations around average velocity, so you see reds and blues. But if you just had a lot of red and you took an average of the entire layer, you'd necessarily then produce a red spot in the red, and everything else would look bluer because it's relative to the average of that layer.
Yeah.
Right, so people come up with these cartoons where they have fast things coming down and slow things coming up. But could you produce the tomography with just the slow thing, or conversely just the fast things?
I don't have a good, I don't think so, but I would have to look at that. We have made synthetic tomography models from our results, and we never did that experiment where we take out the downwellings and only leave the upwellings. In fact, you kind of need the downwellings. You don't have these unless you have these. If you don't have downwellings, this will flatten out into a pile. Yeah. So we haven't done that experiment, but when we do make the synthetic tomography, you do clearly see these, and they look not too different from real tomography. But we haven't done that experiment where we take that out and reproduce it. It would be interesting to do. I've often wondered about that, about this whole, what does that average mean? Like, do you need something on, is the average shifted because you have one thing that's hot or one thing that's cold in there? So, but that's a good question, but I don't know the answer. So I'm going to leave off with a movie made by Ming Ming, who's here. This is from one of his recent papers. And this just gives an idea of our view, at least my view and Ming Ming's view, of what may be going on in the Earth's mantle. Before I start the movie, I should show you what you're going to see. This is the temperature field. So this is a 2D calculation, very high resolution. This is the temperature field. Blue is cold, red is hot. And Ming Ming likes to texturize this a little bit by making the surface, making this a 3D image for a 2D calculation to make it look interesting. So that's why it looks like it pops out a little bit. This is the compositional field. Black would be that green in those cartoons I showed, the depleted Morb source. Cyan here is the more primitive material, so that's the equivalent to purple in the cartoon. And you're going to see oceanic crust come down, and that's going to be yellow in here. Once I tried to make a movie similar to those cartoons, but they're so ugly that those colors were so ugly that you don't want to ever do that. Okay, let's play this. So one thing you notice is plumes form on top of these thermochemical piles, and they entrain stuff. The plumes are sucking these piles up into them. You have background mantle that gets entrained into the piles as well, so you definitely have some interaction between the background and these piles. Oceanic crust comes down, rides up along the top of these things, piles up at times, like here's a little piling up, and then gets flushed into the pile. So all of these components are interacting together, and then everything's getting taken up in mantle plume. So a mantle plume takes in oceanic crust, takes in pile material. It takes in oceanic crust that got flushed into a pile, stirred around for God knows how long, and then coming back out again to see at the surface. So plumes, if this is happening in the Earth, hotspots should see traces of all of this stuff, like young crust, old crust, primitive material, and background mantles. So again, this is just a hypothesis, one hypothesis of what's going on in the Earth's mantle. There's still those other hypotheses as well. Okay, so that's only 1 minute over. I didn't want to cut into Max's time. If anyone has any questions, you can ask me afterwards. I really don't want to cut into Max's time. So, thank you.